Well, good afternoon and happy Monday. Little music before class. So we left off on Friday looking at this problem, and you all worked in breakout rooms to work through this problem. So what I'd like to do is, we didn't finish it, so let's go through and look at this problem here. So you were asked to draw a diagram showing the system and the flow of methane in and out of the valley. So I've drawn a diagram, added a better cow than what I drew on Friday. So we have a situation here where we have airflow into and out of our valley, which we are modeling as a box. You were given a height of the mixing zone. You were given the length, the width, parameters about the number of CAFOs, or combined animal feeding operations, number of animals in each, and the amount of methane produced by each cow. And you were also told the number of wells and the amount of methane produced by each well. You were given a first order rate constant and a concentration of methane entering the valley, along with a velocity at 1/2 the mixing height. So we wrote the general mass balance equation for the fate and transport of methane. So we said that the change in mass with respect to time is equal to the mass rate in plus the mass rate from the CAFOs plus the mass rate from the wells minus the mass rate out minus the mass rate reacted. We then said that the volume is constant. We'll assume that the height, the width, and the length are unchanged during the time period that we're examining. So we can pull volume out of the differential. And we wrote an equation for each of the terms. So we said the mass rate in is equal to the velocity times the concentration entering times the width and the height. So if we go back to this figure here, that was the yellow and the orange. Try to describe, it's the face perpendicular to the wind that is entering or leaving this box. And then the next thing that I asked you to do was to state your assumptions in constructing the mass balance, and looked at a number of your work. Okay, came up, most of you came up with quite a few assumptions. So we just said that the volume is a constant. Okay. We'll also assume that the wind speed at 1/2 the mixing height is also a constant. We'll assume that our emission rates, so the mass rate from the CAFO and from the well are also constant. We'll assume that all wells are operating 24/7, that B is a constant. We'll assume that the system is well mixed. So we have a CSTR. As a number of you mentioned, that will assume that the pollutant enters along one face and leaves from the other face and doesn't leave from any other of the faces on this box. Okay. In assuming that the volume is constant, we're also assuming that this inversion is also constant. We've written this as a first order reaction. So we can assume we have first order kinetics. And we will, because of the problem statement, we will assume that we have steady state. So we can assume that this is a T. It doesn't want to let me write the T. So that the rate of change with respect to time is equal to 0. So those are quite a few assumptions that we can make. And it's important to recognize that these are the assumptions behind the model that we're using. So the next thing we need to do is to determine the steady state concentration. And I changed colors accidentally there, but we'll leave it. So we have U times B now notice I've written this as grams per cubic meter. It was given in milligrams, but everything else, all of our source terms are in grams. So we need to make sure that we have the same units. Same thing with the width and the height. Those were given in kilometers, but we have inverse meters cubed. So make sure you convert those distances to units of meters. And we have 15.2 grams per second. And that was calculated from, and I'll just write it on the top. We have 3 CAFOs, 1,500 cows per CAFO, each cow producing 12.2 grams per hour. And there are 3,600 seconds per hour. Again, make sure your units are consistent. And that is 15.25 grams per second. Our velocity of wind speed is in meters per second. So we want to make sure, again, that our time unit is also seconds. Plus the mass rate from the wells. And there we had 1,420 wells, each well emitting 2.5 grams per second. So that is 3,550 grams per second. Negative, okay. So now those are the masses in. Now we have the masses leaving. So we don't, We don't know the concentration leaving. Remember, the concentration in the reactor is equal to the concentration leaving the reactor because we have steady state conditions, or sorry, not because we have steady state, because we have a completely mixed reactor. And then we have the reaction term, and the reaction rate was given in inverse hours. We need to convert that to inverse seconds. And that is 2.14 times 10 to the minus 7 inverse seconds times C, same C that we have in the previous term, times 4,000 meters times 130 meters times 18,000 meters. And if we solve that for C, that is equal to 0.0041 grams per cubic meter, or 4.1 milligrams per meter cubed. And back in the lecture on climate change, we said that background levels of methane right now are about 1,800 parts per billion. And that is, just to give you a sense of background. And this value here is equivalent to roughly 2,700 parts per billion at 1 atmosphere and 25 degrees C. So just to do a conversion, just to give a comparison. So this would be quite a high level compared to background levels. Any questions?
Could you touch back on the mass balance part of like the volume being constant?
Yes. Okay, so let's just go back here. So this is our box model. We are assuming that we have an inversion layer, and we're going to assume that that inversion layer is constant over the time that we're looking at. So that corresponds to the height. And the width of our valley and the length of our valley won't change because it's the valley. So the only thing really that could change in this situation is that height of that inversion layer. But since we've assumed that it is unchanging, then that means that the volume is constant and we have change in mass with respect to time. Mass is equal to the concentration times the volume. So if our volume is constant, we can pull volume out of the differential, and we have volume times dc dt. So that's that first term on the left-hand side of the mass balance equation. Does that help?
Yeah, it does. Thank you.
Okay. In all of the problems we will do in this class, we will assume volume is constant. That's not obviously not true. We could make this problem extremely complicated. We could have partial differentials in it, but we're not going to do that. We'll assume that volume is constant. Any other questions about this problem? The second part of the problem asks the question, if the hydraulic fracking well suddenly ceased. So if the fracking well suddenly ceased, but the CAFOs operated, what would the concentration be after 2 days? So how do we solve that? So we'll assume that our initial concentration is equal to the 4.1 milligrams per cubic meter, what we just calculated. The source term for the CAFOs, or CAFO, is equal to 15.25 grams per second. That doesn't change. And our time term is 2 days. So if that's the case, we can use the equation that concentration as a function of time is equal to, and this was in one of the previous slides, Q sub S L times U H plus B times 1 minus E to the minus U over L plus K times T plus C0 E to the minus U over L plus K times T. Okay. So we have a term, the initial term that describes really the source, from the source, in this case, the CAFO, and the source from outside the valley, entering the valley, and a term that's related to the initial concentration, which is that 4.1. Now, recognize that Q sub S is equal to Q over L times W. So Q sub S is a term that we use that's specific, that's area specific. So it's our Q in mass per time divided by the area over which the source is dispersed. So if we look at this term here, so we have this term QSL over UH. If we substitute, it's Q L times W times L UH. So the L cancels, and if we're using the mass per time, then that first term becomes U times HW. Apologize for the lines. Give you that sense of how we can relate an area-specific mass or source term to a source term in mass per time. So if we substitute, we have CT is equal to the 15.25 grams per second divided by the 2.4 meters per second times the height times the width plus the plus B. Remember, make sure that's in the same unit. So we want that in grams per cubic meter. So that's that first term. We'll multiply that by 1 minus E to the minus 2.4 meters per second over the length. So we have units of inverse time plus, and the question is, why did I use a plus? The reason is because I have the negative outside of the parentheses, and it's a decay term, both for your wind that's leaving, that's pulling pollutant out of the valley, and there's a negative term outside. It's a loss of pollutant due to reaction. inverse seconds, and I'm going to multiply that, and I apologize for the going on to the next line, but I'm going to multiply that by 2 days, and there were 86,400 seconds per day. Sorry, seconds per day. So, so days cancel and seconds cancel in both cases. Multiple. That's that first term. The second term is 4.1 times 10 to the minus 3. Again, make sure your units are in grams, not milligrams. And we're going to multiply that by e to the minus. And I'm just going to put a parenthesis. That's the same term that exists in the previous term. So it's the same, you can see here, it's the exact same equation. And this is equal to 3.96 times 10 to the minus 3 grams per cubic meter, or 3.96 milligrams per cubic meter. So what does that tell you? What does this tell us here? It was 4.1. So the initial was 4.1 with all the with the CAFOs and the wells. What is the major source of methane in this valley? So with the wells operating, it was 4.1. With all of the wells shut off, it's 3.96. What does that tell us about the source terms? The CAFOs are the main source, exactly. So what we've learned in this situation here is if this were the case, if this were true, then, and these are not that large CAFOs, these are reasonably sized. Methane, the predominant source of methane is from the CAFOs. Any questions? Okay, I have a second problem that we can go through. We can do this in breakout rooms, or I can just go through the problem. Suggestions. Is it helpful to have you go through and look at these problems in breakout rooms? Thoughts, comments? Okay, can I just go through them here? I can do that. So we will do that. Okay. So we have an area source box model for air pollution above a peninsula of land. The width of the box is 15 kilometers. The length is 80 kilometers. And we have a thermal inversion that limits mixing. So we have a mixing height of 15 meters. Air is blowing into, or wind is blowing air into the box at a wind speed of 0.5 meters per second. The concentration of carbon monoxide in the air that's entering is 0.34 milligrams per cubic meter. Between 4 and 6 p.m., there are 150,000 vehicles on the road, and each is driven on average 40 kilometers in that 2 hours, and each is emitting 4 grams of carbon monoxide per kilometer driven. And what we're asked to do is to estimate the concentration of carbon monoxide at 6 p.m. And we'll assume that the concentration at 4 p.m. is equal to that in the incoming air and that carbon monoxide is conservative. We'll assume that mixing in the box is instantaneous and complete, so we have a CSTR. We'll again assume our volume is constant. So we're assuming that the inversion layer doesn't change. We'll assume that U at 1/2 height is constant. So we have a situation here where we have our box. Okay. We'll assume we have air flowing in one side and out the other. Okay. So we're given U, we're told the height, we're told the length, and we're told the width. And we're told that there are actually, I'm going to change this. Let's go back here. This should be a 2. So we have 250,000 cars on the road. Each car is driving 40 kilometers, and each is emitting 4 grams of carbon monoxide per kilometer driven. So that's the constraints that we have. So we can write a mass balance describing the pollutant. So we have, again, the change in mass with respect to time, and that is equal to the mass in through the face plus the mass rate from the cars minus the mass rate out minus the mass rate reacted. But this is equal to 0 because we said that carbon monoxide is conservative. Again, since mass is equal to concentration times volume, and our volume is constant, we can write the equation that's volume times dc dt. And I've stated most of the assumptions. Did I miss any assumption that I previously stated? I changed that to 20. I changed it to 2,500, or 250,000. I apologize. Nope, nobody's bad. My bad, because I should have changed it. Okay. Any other assumptions that, let's see, we said that the volume is constant, CSTR, velocity, the wind speed is constant. Any other assumptions that we need to make? That the 4 grams per kilometer, we'll assume that's an average for all the cars, so that we can average that. Same thing with the 40 kilometers over those 2 hours per car. We'll assume that that's an average. Some will do more, some will less. And we've said that carbon monoxide is conservative. So there are our assumptions. So how do we get Q sub S? We have 250,000 vehicles. each vehicle is traveling 40 kilometers. Each vehicle is emitting 4 grams of carbon monoxide per kilometer driven. So kilometers cancel, vehicles now cancel. This is the traveling over a 2-hour time period. That's the time period. It's 3,600 seconds. And we will divide this by the area. So we have 15 kilometers, so that's 1,500 meters, and 80 kilometers, it's 80,000 meters. So why did I notice here? What I used was the base. So I didn't look at the height at this point. I used the base of our box. Why did I use the base? I'll answer the question about the assumption in just a second. Why did I use the base? I'm averaging over basically where the cars are. So the cars are traveling over this base. So I'm not going to average over the height. When I'm looking at the wind itself, there I'm looking at the wind entering across one face and out the other side. So when you're thinking about where to do the averaging, think about the physics of the system. Cars are driving along the base of the valley, or the base of the peninsula in this case. So we'll divide by the area of that base. Yeah. Cars are traveling along that basis. Okay. In terms of the assumption, so the last assumption I mentioned here was that carbon monoxide is conservative. You're actually told that, and it's, unless you have a very reactive contaminant, we're looking at 2-hour time frame. So that's reasonable for that time frame. And so the equation we're going to use, essentially the same equation that we had here. And actually, I'm going to change this. This really shouldn't be steady state, because we don't know that we achieve steady state in that 2 hours. So the question here is, do we achieve steady state in 2 hours? And the answer is probably not. Okay. Now, so given that, then the equation we'll use is C sub T is equal to Q sub SL over UH plus B, same as before, 1 minus E to the minus U over LT. And notice there's no K term there, plus C sub 0 E to the minus U over L times T. And that is equal to this here is equal to 4.6 times 10 to the minus 6 grams of carbon per meter cubed per second. So that's 4.6 times 10 to the minus 6 grams of carbon divided by times L divided by 2 point, sorry, what was our wind speed? 0.5 meters per second. Okay, sorry. Times the height, which is 15 meters. Now notice, actually, I just realized here, this B term, B was given, let's go back here and look here. Okay, B is given in milligrams per cubic meter. So this is milligrams per cubic meter. Right? I need this in grams. Now this is per cubic meter. And realize we've got a problem here. And I'm actually going to, U is wind speed. B is the concentration entering. And I just realized something and writing this down here. Checking units, because I actually don't have the solution, which is why, if you wondering why I'm over here going, wait a second, what am I doing? And the reason I'm doing this is because I'm over here going, wait a second, there's something wrong with units. Okay, this here is grams per meter cubed per second. Okay, and now I'll be right. So what happens here? Okay. Checking units, because there's an issue with units here. This is actually grams per meter squared. That's our problem. I'm gonna erase this and start over and write it again. So what happens when I don't have notes written properly? And I apologize. So this is in units of grams per meter squared per second. It's grams per second over the area. This then is grams per meter squared per second. So seconds cancel. Okay. And in both cases now, we have units of grams per meter cubed, which is what I was concerned about before, that I didn't have the right units. So the moral of the story here, classmates, mentioned the units problem with the units. We've got the units correct, and now we can add the two. And then this is 1 minus e to the minus this line. So this is minus 0.5 meters per second divided by L times the time. So it's 2 hours times 3,600 seconds per hour. And we solved that, and I actually do not have this solved because I wrote it as a steady state. And really, in 2 hours, you're not going to have steady state conditions. So I will add the answer to this in the notes. Okay. It's going to be around 2 milligrams per, probably around 2.5 milligrams per cubic meter. I'll just write that. So somewhere around 2.5 milligrams per cubic meter. Which just to give you a comparison, the 1 hour standard for carbon monoxide is 40.1 milligrams per cubic meter. So this is the 1 hour carbon monoxide standard. So significantly below that. So that many cars, it sounds like a lot of cars, but that many cars at that carbon monoxide level is actually results in a reasonably low level. So I will fix this in the notes. I will add the correct and final answer. And I apologize that I thought I had my notes and I did not. Any questions about this problem?
I have a quick question. So are we not including the C naught e to the negative u over LT in the answer?
We're not including, no, the C naught is B. Oh, wait, you're right. I didn't include it. So you're right. Plus, thank you. And we said the C naught, thank you for mentioning that. And that is e to the minus u of t. So absolutely, we need to add that to it. So thank you for correcting me on that. So yes, we would need to add the C naught. If we had actually calculated the steady state, which is the solution that I have, which really doesn't make a lot of sense, and that in 2 hours you'd have a steady state conditions. In that case, C naught doesn't matter because it's steady state. But in this case, yes, steady state definitely matters. So thank you for catching that. Right. Any other questions?